Audio Jungle.
Hi, my name is Jayaban Balakrishnan and my supervisor is Dr. Mohammad Inam Abbasi. And I'm pursuing my degree in Bachelor of Electronic Engineering Technology in Telecommunication. I'm here to present my final project, which is development of an expand planar reflector for direct broadcast satellite. So moving on to my introduction. So this is my introduction. Expand planar reflector technology plays a crucial role in a direct broadcast satellite application. This presentation will explore the latest advancement in this field, highlighting improvements in efficiency, design, and performance that enhance satellite communication. Understanding this advancement is essential for future developments in satellite technology. So my next slide is fundamentals of planar reflectors. Planar reflectors are essential components in satellite system, providing high gain and low side lobes. They are designed to reflect signals efficiently, ensuring optimal signal strength and coverage. This slide discusses the basic principles behind the planar reflector design and its importance in satellite communication. So moving on to my literature review, I took up 3 articles which is related to my final year project. So moving to the methodology. So the first step I did is literature review, and then the second one is planar reflector unit cell design. And then once I get the results analysis, I move on to the horn antenna design. And then after done with the horn antenna design, I move on to the periodic planar reflector design and also simulation analysis of a periodic planar reflector. Then move on to radiation pattern results of optimization. When the results are optimized, I then submit to my SV. This slide illustrates design and procedure unit. So these are the steps to construct unit cell. The first thing I did is construct ground, and then move on to the substrate, then move on to the patch. And the last I did extrude for the pot. And now over my right, you can see there's a parameter for FR4 and also Roger. So these are the boundary conditions. So I use magnetic and also electric, and then for Z mean I use open. The next slide illustrate the design and procedure for horn antenna. So this is how I construct my horn antenna. So the material I use aluminum and the type is lossy metal. What I did is I construct through the defined loft and also add a defined brick. So these are the parameters for the horn antenna. So these are the inner dimension of a flare. These are the flare, and these are the inner dimension of a waveguide. So these are my reflector array. These are the steps I use to design my reflector array. So this is the 10 by 10, and over here is 20 by 20. So the 10 by 10 is 150 millimeter, and 20 by 20 is times to 300 millimeter. So moving on to the next slide, the most awaited slide, which is results. So these are the unit cell. So there are 2 types of unit cell I constructed. One's FR4 and one's Roger. You can see the results. This is loss and this is phase. So the right side is from FR4 and the left hand side is for Roger. And this 10 by 10 results. You can see the range is between 8.5 to 9. So this is 10 gigahertz. This is far field, and over here is far field, and the direction is over here. It's omnidirection. And this results for theta, and this is surface current for 10 gigahertz. And this is 20 by 20 reflector array, and that's the result. As you can see, it's all between the range of 8 to 12. So the graph I set is from 8 to 12 because my application is DBS. So the range is between 8 gigahertz to 12 gigahertz. And this for 8 gigahertz and it's far field and direction is over here. As you can see, you can compare the previous result for 8 gigahertz, 10 gigahertz, and 12 gigahertz. And we went to the 10 gigahertz, and this is the results for theta, and this for 12 gigahertz, and this is the max gain, which is the frequency. So and again, the range I set 8 to 12 gigahertz, and then this is the max gain, which is the frequency. So it's the frequency over here, and the max gain. The max gain is up to 3.1. That's the max gain I get for my result. So this is the hardware, which is for 10 by 10. So the material I use is for FR4, and looking at the collaboration with the industry. So we collabs with the Singapore company, which is FP. This is my survey question done for my final project. So, which is I did in the Google form. And these are questions. The first question I asked name and the age. The age is between 18 to 20, 21 to 25, 26 to 35, and then gender, faculty, and this outcome. So this is a pie chart for age. So you can see 40%, which is 18 to 20, is the highest, and gender you can see for 50 is the male. And also for the first question, are you familiar with the concept of direct broadcast satellite? And then many students say no. And the second question, do you think interference is a major issue in the current DPS system? And then majority answers maybe. Have you experienced or studied signal attenuation problems in satellite communication system? And many of them said maybe. Do you believe that improving reflector technology can significantly enhance DPS system performance? Many can see it's a tally for yes and also no. Do you think an expand planar reflector could help reduce interference DPS system? And majority says yes. So based on the survey of on a direct broadcast satellite, which is DBS system and reflected technology, so it is evident that many participants are not fully aware of advancements of potential improvement on DBS system. So particularly with regard of expand planner factors, three suggestions for increasing awareness. The first one is education workshop and seminars. The second suggestion is online webinars and tutorials. The third one is collaborate with the academic institution. Okay. Last but not least, in conclusion, advancement in expand planar reflector technology are pivotal for evolutions of direct broadcast satellite. Continued research and development will likely to lead to further enhancement in performance and efficiency, paving the way for more robust satellite communication system in the future. That's all from me. Thanks.